The periodic table is a tabular arrangement of the chemical elements, ordered by their atomic number, electron configurations, and recurring chemical properties. The table also shows 4 rectangular blocks, S, P, D and F block. In general, within one row the elements are metals on the left-hand side, and non-metals on the right-hand side. The rows of the table are called periods, the columns are called groups. 6 groups have names, as well as numbers. For example, group 17 elements are the halogens, and group 18, the noble gases. The periodic table can be used to derive relationships between the properties of the elements, and predict the properties of new elements yet to be discovered or synthesized. The periodic table provides a useful framework for analyzing chemical behavior, and is widely used in chemistry and other sciences. Dmitri Mendeleev published in 1869 the first widely recognized periodic table. He developed his table to illustrate periodic trends in the properties of the then-known elements. Mendeleev also predicted some properties of then unknown elements that would be expected to fill gaps in this table. Most of his predictions were proved correct when the elements in question were subsequently discovered. Mendeleev's periodic table has since been expanded and refined with the discovery or synthesis of further new elements and the development of new theoretical models to explain chemical behavior. All elements from Atomic Numbers Chapter 1 to 118 have been discovered or synthesized, with elements 113, 115, 117, and 118 having been confirmed by the Iupac on December 30, 2015. The first 94 elements exist naturally, although some are found only in trace amounts and were synthesized in laboratories before being found in nature. Elements with atomic numbers from 95 to 118 have only been synthesized in laboratories. It has been shown that elements 95 to 100 once occurred in nature, but currently do not. Synthesis of elements having higher atomic numbers is being pursued. Numerous synthetic radionuclides of naturally occurring elements have also been produced in laboratories. Overview. Each chemical element has a unique atomic number representing the number of protons in its nucleus. Most elements have differing numbers of neutrons among different atoms, with these variants being referred to as isotopes. For example, carbon has 3 naturally occurring isotopes. All of its atoms have 6 protons and most have 6 neutrons as well, but about 1% have 7 neutrons, and a very small fraction have 8 neutrons. Isotopes are never separated in the periodic table, they are always grouped together under a single element. Elements with no stable isotopes have the atomic masses of their most stable isotopes, where such masses are shown, listed in parentheses. In the standard periodic table, the elements are listed in order of increasing atomic number. A new row is started when a new electron shell has its first electron. Columns are determined by the electron configuration of the atom. Elements with the same number of electrons in a particular subshell fall into the same columns. Elements with similar chemical properties generally fall into the same group in the periodic table, although in the F block, and to some respect in the D block, the elements in the same period tend to have similar properties as well. Thus, it is relatively easy to predict the chemical properties of an element if one knows the properties of the elements around it. As of 2016, the periodic table has 118 confirmed elements, comprising elements 1 to 118. Elements 113, 115, 117 and 118 have been officially confirmed by the International Union of Pure and Applied Chemistry in December 2015. Though their official names are yet undecided. As such, these elements are currently identified by their atomic number, or by their provisional systematic name. A total of 94 elements occur naturally. The remaining 20 elements, from americium to copernicium, and flerovium and livermorium, occur only when synthesized in laboratories. Of the 94 elements that occur naturally, 84 are primordial. The other 10 naturally occurring elements occur only in decay chains of primordial elements. No element heavier than einsteinium has ever been observed in macroscopic quantities in its pure form, nor has astatine. Francium has been only photographed in the form of light emitted from microscopic quantities. Grouping methods. Groups. A group or family is a vertical column in the periodic table. Groups usually have more significant periodic trends than periods and blocks, explained below. Modern quantum mechanical theories of atomic structure explain group trends by proposing that elements within the same group generally have the same electron configurations in their valence shell. Consequently, elements in the same group tend to have a shared chemistry and exhibit a clear trend in properties with increasing atomic number. However, in some parts of the periodic table, such as the D block and the F block, horizontal similarities can be as important as, or more pronounced than, vertical similarities. Under an international naming convention, the groups are numbered numerically from 1 to 18 from the leftmost column to the rightmost column. Previously, they were known by Roman numerals. In America, the Roman numerals were followed by either A if the group was in the S or P block, or A, B if the group was in the D block. The Roman numerals used correspond to the last digit of today's naming convention. In Europe, the lettering was similar, except that A was used if the group was before group 10, and B was used for groups including and after group 10. In addition, groups 8, 9 and 10 used to be treated as one triple-size group, known collectively in both notations as group 8. In 1988, the new Iupac naming system was put into use, and the old group names were deprecated. Some of these groups have been given trivial names, as seen in the table below, although some are rarely used. Groups 3 to 10 have no trivial names and are referred to simply by their group numbers or by the name of the first member of their group, since they display fewer similarities in, or vertical trends. Elements in the same group tend to show patterns in atomic radius, ionization energy, and electronegativity. From top to bottom in a group, the atomic radii of the elements increase. Since there are more filled energy levels, valence electrons are found farther from the nucleus. From the top, each successive element has a lower ionization energy because it is easier to remove an electron since the atoms are less tightly bound. Similarly, a group has a top-to-bottom decrease in electronegativity due to an increasing distance between valence electrons and the nucleus. There are exceptions to these trends, however, an example of which occurs in group 11 where electronegativity increases farther down the group. Period. A period is a horizontal row in the periodic table. Although groups generally have more significant periodic trends, there are regions where horizontal trends are more significant than vertical group trends, such as the F block, where the lanthanides and actinides form two substantial horizontal series of elements. Elements in the same period show trends in atomic radius, ionization energy, electron affinity, and electronegativity. Moving left to right across a period, atomic radius usually decreases. This occurs because each successive element has an added proton and electron, which causes the electron to be drawn closer to the nucleus. This decrease in atomic radius also causes the ionization energy to increase when moving from left to right across a period. The more tightly bound an element is, the more energy is required to remove an electron. Electronegativity increases in the same manner as ionization energy because of the pull exerted on the electrons by the nucleus. Electron affinity also shows a slight trend across a period. Metals generally have a lower electron affinity than nonmetals, with the exception of the noble gases. Blocks. Specific regions of the periodic table can be referred to as blocks in recognition of the sequence in which the electron shells of the elements are filled. Each block is named according to the subshell in which the last electron notionally resides. The S block comprises the first two groups as well as hydrogen and helium. The P block comprises the last six groups, which are groups 13 to 18 in Iupac, and contains, among other elements, all of the metalloids. The D block comprises groups 3 to 12 and contains all of the transition metals. The F block, often offset below the rest of the periodic table, has no group numbers and comprises lanthanides and actinides, metals, metalloids and non-metals according to their shared physical and chemical properties. The elements can be classified into the major categories of metals, metalloids and non-metals. Metals are generally shiny, highly conducting solids that form alloys with one another and salt-like ionic compounds with non-metals. The majority of non-metals are colored or colorless insulating gases. Non-metals that form compounds with other non-metals feature covalent bonding. In between metals and non-metals are metalloids, which have intermediate or mixed properties. Metal and non-metals can be further classified into subcategories that show a gradation from metallic to non-metallic properties. When going left to right in the rows, the metals are subdivided into the highly reactive alkali metals, through the less reactive alkaline earth metals, lanthanides and actinides, via the archetypal transition metals, and ending in the physically and chemically weak post-transition metals. The non-metals are simply subdivided into the polyatomic non-metals, which, being nearest to the metalloids, show some incipient metallic character, the diatomic non-metals, which are essentially non-metallic, and the monatomic noble gases, which are non-metallic and almost completely inert. Specialized groupings such as the refractory metals and the noble metals, which are subsets of the transition metals, are also known and occasionally denoted. Placing the elements into categories and subcategories based on shared properties is imperfect. There is a spectrum of properties within each category, and it is not hard to find overlaps at the boundaries, as is the case with most classification schemes. Beryllium, for example, is classified as an alkaline earth metal, although its amphoteric chemistry and tendency to mostly form covalent compounds are both attributes of a chemically weak or post-transition metal. Radon is classified as a non-metal and a noble gas, yet has some cationic chemistry that is more characteristic of a metal. Other classification schemes are possible, such as the division of the elements into mineralogical occurrence categories, or crystalline structures. Categorizing the elements in this fashion dates back to at least 1869, when Hinrichs wrote that simple boundary lines could be drawn on the periodic table to show elements having like properties, such as the metals and the non-metals, or the gaseous elements. Periodic trends. Electron configuration. The electron configuration or organization of electrons orbiting neutral atoms shows a recurring pattern or periodicity. The electrons occupy a series of electron shells. Each shell consists of one or more subshells. As atomic number increases, electrons progressively fill these shells and subshells more or less according to the Madelung rule or energy ordering rule, as shown in the diagram. The electron configuration for neon, for example, is 1s2 to s22p6. With an atomic number of 10, neon has 2 electrons in the first shell, and 8 electrons in the second shell, 2 in the s subshell and 6 in the p subshell. In periodic table terms, the first time an electron occupies a new shell corresponds to the start of each new period, these positions being occupied by hydrogen and the alkali metals. Since the properties of an element are mostly determined by its electron configuration, the properties of the elements likewise show recurring patterns or periodic behavior, some examples of which are shown in the diagrams below for atomic radii, ionization energy and electron affinity. It is this periodicity of properties, manifestations of which were noticed well before the underlying theory was developed, that led to the establishment of the periodic law and the formulation of the first periodic tables. Atomic radii vary in a predictable and explainable manner across the periodic table. For instance, the radii generally decrease along each period of the table, from the alkali metals to the noble gases, and increase down each group. The radius increases sharply between the noble gas at the end of each period and the alkali metal at the beginning of the next period. These trends of the atomic radii can be explained by the electron shell theory of the atom. They provided important evidence for the development and confirmation of quantum theory. The electrons in the 4f subshell, which is progressively filled from cerium to terbium, are not particularly effective at shielding the increasing nuclear charge from the subshells further out. The elements immediately following the lanthanides have atomic radii that are smaller than would be expected and that are almost identical to the atomic radii of the elements immediately above them. Hence hafnium has virtually the same atomic radius as zirconium, and tantalum has an atomic radius similar to niobium, and so forth. This is known as the Lanthanide Contraction. The effect of the Lanthanide Contraction is noticeable up to platinum, after which it is masked by a relativistic effect known as the inert pair effect. The D block contraction, which is a similar effect between the D block and P block, is less pronounced than the Lanthanide contraction, but arises from a similar cause. Ionization energy. The first ionization energy is the energy it takes to remove one electron from an atom. The second ionization energy is the energy it takes to remove a second electron from the atom, and so on. For a given atom, successive ionization energies increase with the degree of ionization. For magnesium as an example, the first ionization energy is 738 kilojoules per mole and the second is 1450 kilojoules per mole. Electrons in the closer orbitals experience greater forces of electrostatic attraction, thus, their removal requires increasingly more energy. Ionization energy becomes greater up and to the right of the periodic table. Large jumps in the successive molar ionization energies occur when removing an electron from a noble gas configuration. For magnesium again, the first two molar ionization energies of magnesium given above correspond to removing the two 3s electrons, and the third ionization energy is a much larger 7,730 kilojoules per mole, for the removal of a 2p electron from the very stable neon-like configuration of Mg2+. Similar jumps occur in the ionization energies of other third-row atoms. Electronegativity. Electronegativity is the tendency of an atom to attract electrons. An atom's electronegativity is affected by both its atomic number and the distance between the valence electrons and the nucleus. The higher its electronegativity, the more an element attracts electrons. It was first proposed by Linus Pauling in 1932. In general, electronegativity increases on passing from left to right along a period, and decreases on descending a group. Hence, fluorine is the most electronegative of the elements, while cesium is the least. At least of those elements for which substantial data is available. There are some exceptions to this general rule. Gallium and germanium have higher electronegativities than aluminium and silicon respectively because of the D block contraction. Elements of the fourth period immediately after the first row of the transition metals have unusually small atomic radii because the 3d electrons are not effective at shielding the increased nuclear charge, and smaller atomic size correlates with higher electronegativity. The anomalously high electronegativity of lead, particularly when compared to thallium and bismuth, appears to be an artifact of data selection. Methods of calculation other than the Pauling method show the normal periodic trends for these elements. Electron affinity. The electron affinity of an atom is the amount of energy released when an electron is added to a neutral atom to form a negative ion. Although electron affinity varies greatly, some patterns emerge. Generally, nonmetals have more positive electron affinity values than metals. Chlorine most strongly attracts an extra electron. The electron affinities of the noble gases have not been measured conclusively, so they may or may not have slightly negative values. Electron affinity generally increases across a period. This is caused by the filling of the valence shell of the atom. A group 17 atom releases more energy than a group 1 atom on gaining an electron, because it obtains a filled valence shell and is therefore more stable. A trend of decreasing electron affinity going down groups would be expected. The additional electron will be entering an orbital farther away from the nucleus. As such, this electron would be less attracted to the nucleus and would release less energy when added. However, in going down a group, around 1/3 of elements are anomalous, with heavier elements having higher electron affinities than their next lighter congeners. Largely, this is due to the poor shielding by d and f electrons. A uniform decrease in electron affinity only applies to group 1 atoms. Metallic character: the lower the values of ionization energy, electro negativity and electron affinity, the more metallic character the element has. Conversely, non-metallic character increases with higher values of these properties. Given the periodic trends of these three properties, metallic character tends to decrease going across a period and, with some irregularities due to poor screening of the nucleus by d and f electrons, and relativistic effects, tends to increase going down a group. Thus, the most metallic elements are found at the bottom left of traditional periodic tables and the most non-metallic elements at the top right. The combination of horizontal and vertical trends in metallic character explains the stair-shaped dividing line between metals and non-metals found on some periodic tables, and the practice of sometimes categorizing several elements adjacent to that line, or elements adjacent to those elements, as metalloids.